In this video, let's briefly bring together the different clustering algorithms that we've introduced and discuss some of the pros, the cons, and the use cases for each one. So what will we cover here in this section? In this section, we'll go over a review of the clustering approaches that we went through throughout this course. We'll then summarize and compare each one of these different approaches, as well as providing some guidelines for choosing which approach is best given the business case that you are working with. So let's review the clustering algorithms discussed in this course so far. First we have k-means, and recall that with k-means we were going to have to predetermine that number of clusters that we're looking for. And once we do so, our clusters will depend on coming up with some mean value that is trying to reduce the distance from our centroids, or that mean of that cluster, to each one of the different points within that cluster. With that in mind, we will get the results that we see here for the shapes given, and we see that it doesn't do a perfect job of getting shapes that aren't necessarily spherical. And we're going to dive a bit deeper into the pros and cons of each in just a bit. But this is just a recap and an intro to what we're working with each of the models that we had introduced. So next, we have the mean shift, which does not require us to set that number of clusters as we had to do with k-means, but rather will iteratively move towards those densest points given a window, and we'll get the results that we see here under mean shift. And notice that for both k-means and mean shift, they're going to heavily favor more of a spherical shape and may not have quite the flexibility to find different shapes. Next we have Ward, and what we mean here by Ward is the agglomerative hierarchical clustering with Ward as the linkage type between our clusters. Recall that Ward linkage specifies distance between clusters as the new combined inertia of those clusters. And since we are linking closest clusters when we work with hierarchical clustering, we have a bit more flexibility in combining clusters of different shapes. But some noise can throw this off, as it did in our two circles example above. And while we can set means of how we want clusters determined, they do not quite get determined on their own accord as we saw with mean shift, or as we will see in this next one with dbScan. So finally we have dbScan, which will find those points which are closest to one another in order to create those clusters. And this will both create its own clusters, so you don't have to predetermine the number of clusters, and be able to identify clusters of different shapes. Now this may seem like dbScan should always be the one to go with, but we'll dive a bit deeper into what can make dbScan a bit more difficult and at times not the ideal candidate. So let's dive deeper, starting with k-means. With k-means, if we use minibatch to find our centroids and clusters, this will find our clusters fairly quickly, so it'll run with fairly low complexity compared to the other models. If we don't already know how many clusters we are looking for, with k-means we're going to have to search through our k-values and use something like our elbow method that we introduced to determine that number of clusters. It'll generally be a bit more skewed to finding even-sized clusters when we work with k-means. And it's not going to work well with non-spherical cluster shapes, as we'll be looking at distance from the centroid in every single direction as we move towards that mean, and therefore we'll only be able to find more spherical shapes, which is why it doesn't do a great job with these different shapes that we have here. Next we have mean shift, and with mean shift we do not have to guess k. The number of clusters will be determined for us. Also, mean shift will do a fairly good job of finding uneven cluster sizes. It'll simply be moving towards that highest density given a specified bandwidth so we can find uneven clusters. They don't have to be even in any means, such as what we saw with k-means. Now it can be slow with a lot of data. We said that k-means with the minibatch can run very fast. The mean shift can tend to be a bit slow if we have a lot of data, as it's going to be searching for points for highest local density for every single point. It will do a good job of finding a lot of clusters if they exist in the dataset. So if you think that there are a lot of clusters, this may be a good choice. It will not do a great job of finding weird shapes, as again, we are looking for closeness in every direction within a certain window, so it'll tend to go towards more spherical shapes. And it will be limited to using the Euclidean distance within its formulation. So we don't get to use these other metrics, these other distance metrics that we introduced earlier in the course. Now we move to hierarchical clustering, here with Ward. And the strength of hierarchical clustering really comes into play when we want to get a full hierarchy tree and see how some groups may be subgroups of others. Now, you do have to come up with some means of deciding the number of clusters on your own, whether that's choosing the numbers directly or with a minimum average distance threshold, as we saw in our course on hierarchical clustering. It will often find uneven cluster sizes, as we can easily have a tiny cluster of 1 or 2 points that are far away from the rest. There are going to be many different distance metrics and linkage options that can be chosen, which may make it difficult to fine-tune this type of model. And it can end up being very slow to calculate as the number of observations increases. So this also will have fairly high complexity. Now with dbScan, it seems you can often get the best of both worlds if you choose the right parameters. But finding those correct parameters can prove to be a difficult task. Now with dbScan, it will be able to find clusters of uneven sizes. As long as it reaches the n-clue amount that was predefined, it will create a new cluster, assuming again that you have, if n-clue is equal to 4, as long as you have 4 points within that epsilon radius, you will create a new cluster. It will work with distance metrics of your choosing, so you're not limited to just Euclidean distance. dbScan will be able to easily move along a cluster in small steps, thus being able to find clusters of uneven shapes. Now there is a danger, if you choose too small of an epsilon, that you will have too many clusters, which is probably not ideal or trustworthy for most business cases. And finally, the main disadvantage is that it can have a great difficulty determining clusters of different densities. Now to bring it all together, I would say take a look at this page if you're ever trying to decide which one of the different clustering approaches to use. If you look at the parameters for k-means, you just need to choose the number of clusters. Mean shift bandwidth, which may be a little bit difficult to fine-tune. For hierarchical clustering, you choose the number of clusters, but you can also visualize the clusters that are created as they grow one on top of the other. So it becomes a bit easier to choose that number of clusters. And then the neighborhood size could be fairly difficult to choose when you're working with dbScan. Now the scalability of each. With k-means, you can scale to very large number of samples, so very large data. You probably want a medium amount of clusters, not too many clusters. And this is both using mini-batch, which will help speed things along. Mean shift will not be quite as scalable with the number of samples. So as we increase the number of samples, it tends to take quite some time. The complexity increases. With hierarchical clustering, you can use large, so not very large like k-means, but large number of samples as well as a large number of clusters. And then dbScan again will scale quite large number of samples and a medium amount of clusters. Now, we have here the different general use cases, but I want to skip more to the applications. All I want to highlight for the general use cases is that again with dbScan you can also use it for outlier detection. Unlike the others, it'll do a good job of determining those outliers. Now in regards to the applications, we have that for k-means, you can find few clusters of roughly the same size. I would say this is a quick and dirty way. If you know the number of clusters that you're looking for, then this may be a good way to get started in your clustering of your dataset. With mean shift, you can identify the number of clusters on its own. So if you don't know the number of clusters, this is a good choice, often used in video. And also, again, if you don't know those clusters, this is a good for a business case, especially if dbScan may be difficult to fine-tune or if you have clusters of different densities. And then hierarchical clustering will be good for business cases where you may want to find the subgroups as well. So if you don't just want the groups, but the subgroups that build into those groups. And then finally, dbScan, that's often used for computer vision applications, but also for business cases where you don't know the number of clusters and they are of similar density. Then you can use dbScan to identify those clusters for you. So just to quickly summarize, what we went through here were different clustering techniques, where clustering is just unsupervised learning, meaning we don't have labels, but we can come up with groupings of our data to see if there's different segments of our data that can be clumped together. And we discussed several approaches that were possible, such as k-means, hierarchical agglomerative clustering, dbScan, mean shift, and all of this can be implemented using sklearn. And if you're interested in learning more about the different hyperparameters that can be passed through, or even more clustering methods, I would suggest looking at the link, and feel free to dive deeper and experiment with everything that you have there available. Now, just to recap, in this section, we had a review of the different clustering approaches that we've discussed throughout this course. We summarized and compared each one of the different clustering approaches, and then finally provided some guidelines for choosing which approach is appropriate for the given business situation. That closes out our section here on clustering, and in the next videos, we will move on to dimensionality reduction. All right, I'll see you there.